Let's see if others will join for half a minute, and then let's start the second part of hypothesis testing. Okay, so let's start. Today we will continue with hypothesis testing. In this part, we will really look at testing means or testing differences in means, which will be related to one sample t-test, all kinds of t-tests and ANOVA. And finally, we will look at correlation analysis. So let's start with t-test. In both t-test and ANOVA, we are interested in the mean. And as I said last time, we are interested in understanding this population true value, population mean, but we only have a sample. So we want to understand from our sample and sample mean if we can generalize this to the general population that we are interested in. Here we will look at if, for instance, if we have just one sample and we hypothesize a mean based on theory or based on some practice, and we will compare it with that, we will call that a one sample t-test. There is also what's called a pair t-test, where you have measurements from the same people or same elements, and you do measurements like now and I don't know, a couple of months later or a couple of years later. You can also think it as I don't know, you look at political affinity before and after an election, for instance, and you want to understand how this the mean of this political affinity actually changes before and after an election. Or you might actually have two different ways of asking the same question, and you are kind of comparing if these are measuring the same thing or different things, etc. But the main thing, main identification here is that you are actually measuring the same, same people, measuring from same people or same elements. Then, if we have groups in the data, so we would call this independent samples. Like we talked about gender last time, it could be also related to, if you are doing a research in different types of building architecture, for instance, it might be that you are interested in splitting these in neighborhoods. That can also be an independent sample. And then you basically want to compare the means among these groups. If you have two groups, if you have two independent groups, then this will be an independent samples t-test or two sample t-test. And then if we have more than two independent samples, we will use a one-way ANOVA. And I will go over that, all of them now. Let's start with one sample t-test. So in one sample t-test, the purpose is to test the mean of the population, again, as I said, from which the sample is drawn. And you want to understand if the sample, like what you see in the sample, the population mean is actually equal to a comparison standard. So it's a certain value. And then this value comes from, it has a theoretical basis, or as I said, it comes from practice. In the purpose of the course, basically, this is something given to you somewhere in the text if there is a question related to one sample t-test. And then, of course, as you know, we can only look at the mean if we have a metric variable. So that is also another way to kind of identify that you need to use a t-test. So it should be ratio or interval. And there are still some assumptions, as I mentioned before. For instance, the sample has to be random and representative. Like at the end of the sampling, we said that, okay, we have non-probability sampling and probability sampling. And then all of these methods of hypothesis testing assumes random sampling. So that's one thing. And for instance, another one is that we assume the variable that we are interested in. So the mean perception of a brand, for instance, then we assume that our measurement of this brand perception is normally distributed. And the hypothesis for the one sample t-test is related to the mean, as I said. So we say the mean is equal to, less than, or equal, or more than or equal to some given number. And then H1 would be the mean of our sample is not equal to higher than or lower than a particular value. So here, this equal to, as we saw yesterday, the mean is equal to 5, for instance, would be a two-sided hypothesis. But if you have less than or equal to or more than or equal to in H0, this would be a one-sided test. Let's now look at an example. So a researcher wants to characterize his participants' level of depression. Okay, he tested each participant on a particular depression index where anyone who receives a score of 4 is deemed to have normal levels of depression. Lower scores indicate less depression and higher scores indicate greater depression. The study involved 40 participants. So you generally have this indication of the sample size because as we have more and more sample size, the distribution is generally normal, the distribution of the mean at least. So if you have heard central limit theorem, this is where it starts to kick in, basically. Then the question is the sample representative of the population? So do they score statistically significant different from 4, which was deemed to have normal levels of depression, for instance? So we will have a comparison of the mean from our measurements and this depression index. We will compare those two. And our level of significance is 0.05, as we do in general. So we have our data, data frame, we read it into R, and then we look at the depression score, which is the column that we are interested in. Okay, so if you look at the mean, apparently this is quite close to 4, actually 373, but these are all, this part is all descriptive. And then we can also look at the standard deviation to see how variable is this depression score in our measurements. And here in this box plot, you can also see that there's actually variability around the median of this depression scores. So we see that it's actually lower than the population, but it's also quite close to 4. We can, of course, formally test this with a t-test. So we basically put the column here, and then mu is equal to 4. Okay, there's a question how to read the box plot. Yes, the box plot basically shows you the variability in the data. This little part is the median, and then this like upper and lower quantiles, upper and lower quartiles, sorry. So you basically split your data into 4. This is the middle 50% of the data. This is your median. And then these are the 75 and 25 percent points. But essentially, you look at how variable is your data with a box plot. So the mu is equal to 4 because here in the text, the question was, is the sample representative of the population? We apparently know from the population that the normal levels of depression is 4. So we want to understand if this representatives of the population is achieved in our sample. So that's why we put 4 here. So this is basically a theoretically known value in the population. Okay, so we write this line of code and we get our results. So here you have the test statistic, which is a t value, degrees of freedom, and p-value. We focus on the p-value to make our conclusion. You can also use the t-value if you want to. Because our significance level was 0.05 and this p-value is smaller than that, we reject H0. And in this case, H0 is that this depression score, the mean depression score in the population is 4. And our sample, from our sample, we also see that, from our sample, we actually reject it, meaning that we conclude that the depression score in the population based on our sample, meaning that what we can infer from our sample is that this value is different than 4. So in this sense, in this case, we can also look at 95% confidence interval as well. This is exactly one-to-one with 0.05 significance level, if you remember. So this this confidence interval does not include 4. And the mean of X is 3.73, as we also measured here. So these are the things that you can read from this output. The conclusion is that we reject H0 and conclude alternative hypothesis. And in this case, the alternative hypothesis is that this depression score in our sample is different than 4. Okay. So this basically our sample does not achieve this theoretical value, meaning that our sample is not representative for this question. Good question. When you have t-test, there are default options for all of the parameters. So you don't see all of the parameters that this function takes. And then you basically, the default option for the t-test function is significance level 0.05. If this changes, then you can basically, yeah, I mean, you see that this will always give 95% confidence interval. It doesn't matter actually the significance level because it returns a p-value. So you always have to judge for yourself based on the significance level that you're seeking. So if the significance level was 0.01, this is higher than 0.01, and then we would not be able to reject the null hypothesis. Does that make sense? But you will always get this 0.0, that the results here based on the 0.05 significance. So this will always be 95% confidence interval, and this will always be the conclusion based on 0.05. So pay attention to that. I mean, pay attention to the significance level and the result. 395 is rounded up to 4. Yes, but of course we are being more precise here. So this 4 means actually 4.00000. Do we have to focus on the mean of X to conclude the mean is not 4? No, you don't have to focus on that. This just gives you an indication of the side, which side of 4 it is actually. But this is a two-sided test, right? We will also see a one-sided test soon. But the default option in t-test, if you don't write anything else, is a two-sided test. So in the two-sided case, you just conclude if it's 4 or not. So in that sense, p-value is just the indicator here that you should focus on. You reject at 1% level, not reject at 5% level. It's the other way around. So we reject if p-value is very small, right? If you remember, we had this distribution of normal, and then if what we see in the sample is very extreme in this distribution, then we would actually reject the null hypothesis, because this distribution we kind of drove it by assuming the null hypothesis is true. So the rule is that if the p-value is less than your significance level, then you reject the null hypothesis, because the value that you see is extreme under the null distribution. So if the significance level is 1%, then because this is greater than 1%, this doesn't cut the mark. Then you do not reject. But for the 5%, it's below 0.05. Why is it a two-sided test? This is the default option in the t-test function. So we could have also done a one-sided test, but then we also need to add an argument here, an additional argument. So in any function in R, you always have parameters of the function, meaning that like in the first, like before the first comma, you need to put your data. If you have a mu equal to something, then it will understand that this is a one sample test. And then if you don't put anything else, the default option here is that it is a two-sided test. So in R, you would also have, for instance, if you do a one-sided test, which we will see soon, you put an alternative equal to less or greater here. Yeah, if you don't see anything related to alternative argument here, which is the alternative hypothesis, then this is always a two-sided test. Okay. So the pair simple t-test. In this case, we want to understand, we want to compare two means, okay? Previously, we had one value that we know from theory or know from this depression index, and we had just one mean from our sample. In this case, we actually have two means, but these mean scores are related to the same people or same observations or same elements. As I said, this can be different measures different measures trying to measure the same thing, or same measures different times, measured at different times. So you test whether the difference between two scores is significantly different from 0. This is for everyone in your sample then. So you have, in this case, this depiction is related to same measure at different times. You want to understand for everyone what's the difference between the measures here, and you compare the means again. So the null hypothesis here is that the mean of the difference, so the mean difference between two scores in our sample is equal to 0. The mean of difference between two scores is not equal to, higher than, or lower than. So the hypothesis, here I should also add probably like lower than or equal to and higher than or equal to. So this can also be a one-sided null hypothesis or a one-sided the alternative hypothesis. The way you actually execute this in R is related to what we have just seen. So remember that here we are saying that, for instance, mu1, mu being the mean, mu1 is greater than mu2, for instance, or mu1 is not equal to mu2. Okay, the mean of the first measurement is different than the mean of the second measurement for the same sample. So for that, we actually construct a new variable. So we take the difference between the two and then test with one sample t-test. So we test the difference between the two means, but using one sample t-test. We can also talk about how would you formulate H0 and H1 of a paired sample t-test as a one-sided hypothesis. I think I have provided the alternative hypothesis here, but what would be, for instance, if you can write what would be the null hypothesis if the alternative hypothesis is that the mean of difference between two scores in our sample is higher than 0. Does anyone have any idea? Yes, equal to or less than. I see one. And yeah, it's indeed equal to or less than. As we talked last time, the hypotheses are mutually exclusive, meaning that if the alternative hypothesis is higher than, then H0 has to be lower than or equal to or less than. And remember that H0 is the alternative that is the hypothesis that always includes 0 or equality. Okay, let's now look at how we do this in R with an example. So the situation is that a multinational corporation measured employee satisfaction at the end of 2022 and 2023 by asking all employees to fill out a survey. They want to understand whether the average satisfaction changed between 2022 and 2023. So I hope this is kind of giving you already the indication that, okay, we have two different measurements of the same thing, and we want to understand if the average satisfaction, which is the mean, right, changed between these two times. Then our null hypothesis is that the mean satisfaction of the dependent groups are equal to each other. Yeah, and in this case, dependent groups meaning the employees. The mean satisfaction of the dependent groups are not equal to each other is the alternative hypothesis. If we if there is a one-sided or two-sided test that we are seeking from you, we will always have more indications here. So don't worry about that too much. Just know that in the case of two-sided, you have equality and inequality. In a one-sided test, you would always have this directionality and equality here, and just directional difference between the two. Okay, so there is also another there's also another case. For instance, we will see this in a couple of minutes. In a recent survey, a multinational corporation measured satisfaction with the company and satisfaction with the department. You saw that there's a high correlation between the two, and you wonder whether respondents differ significantly in their satisfaction with the company and their department. This is this was the same measure, same survey in different times. This is an example of what you can see. For instance, in the case of you use the same subjects again, same participants, but you have this satisfaction with the company, satisfaction with the department. If these two actually differ, then you still use a pair t-test. In this case, then your null hypothesis is that the means of the two variables are equal to each other again, or the means of the two variables are unequal to each other. And both of them you can do with one sample t-test, and this you will actually do in the assignment. So please observe that you can actually convert these hypotheses into a different statements. So the means of the two variables are equal to each other, meaning that the difference between the two variables has a mean equal to 0. mu1 minus mu2 equal to 0. If you just take this mu2 on the left-hand side, then it will be mu1 minus mu2 equal to 0, right? And if you do the same thing for h1, you can also state this as the difference between the two variables has a mean unequal to 0. What's a t-test you would most likely use during your thesis? I would say that would be a two-sample t-test, which independent samples t-test, which we will see now. But again, there might be cases if you are doing like if you are doing two measurements, or if you are doing if you basically ask questions that are quite similar to each other, or you ask questions which you think that they are different, like they are measuring different things, but it looks like they don't, like their means are very close to each other, for instance, then you might also want to use a paired sample t-test. So all of these might occur in your thesis. I would say one sample tests are just simpler, so I don't see that happening in a thesis. But the two sample, like independent samples and dependent sample t-tests might occur. And also ANOVA, of course, if you have more than two groups. Okay, let's look at the independent t-test, independent sample t-test, or two sample t-test, as it might be, it's called in other sources. Here, the purpose is to compare mean scores of two different and independent groups of people or elements, or basically observations. This is, indeed, if you see, and the groups then are either nominal or ordinal, right? If you have a grouping variable, this is nominal or ordinal, but you have the mean, which means that your dependent variable is metric. So we want to understand, for instance, if the like the satisfaction with the university is the same for all of the, or satisfaction with the IBA program is different for class 1 and class 2, for instance. The thing is that we always have two for the t-test, two groups. Okay, the difference between independent samples t-test and pair t-test is that in the independent samples, as the name indicates, you have independent samples. So when I compare, let's say, okay, maybe this is a good example that, let's say the university handed out you a survey in the first year, at the end of the first year, and they hand out the same survey at the end of the second year. And we want to understand the mean satisfaction, if the mean satisfaction has changed. So we can make a paired sample t-test if I compare the mean across all of the students in both years. notice that like we are actually using the same participants in this case. Okay, I'm assuming everyone answered this survey in both years. I'm using the same subject, but the measurement time differs, for instance. And it might be the first example that I said, that I want to compare the satisfaction in the first year students and the second year students. Then I'm actually using the data from the first year and the second year students in a separate manner, right? Like I calculate the mean across the first year students and mean across the second year students, which means that these are independent samples. I hope that makes sense. Okay, so yeah, that also kind of summarizes the purpose of the two samples or independent samples t-test. We again have the assumption of normal distribution for the data. And then you can formulate the hypothesis for this t-test based on the differences. So the mean difference of the two groups is equal to 0, or mean difference of the two groups is not equal to 0. And then, sorry, the mean difference of the two groups is not equal to 0, or you can formulate this in terms of the means. So the two means of the two groups are equal, meaning that, I mean, I hope you see that these are actually stating the same things. If the difference between the means is equal to 0, it means that these means are equal. And the alternative hypothesis in this case would be the mean of one group is higher or lower than that of the other group, or not equal to. So I should update these more to not confuse you. But the point is here that if you have a one-sided null hypothesis, then alternative hypothesis should be, what did I say, one-sided. So if the null hypothesis is two-sided, meaning that we are talking about only an equality, in this case we do, then the alternative hypothesis should be related to inequality. So the mean of one group is not equal to the other group is the correct alternative hypothesis, just to show you that. So here, if we are talking about are equal, correct one is not equal. And then if we have higher, then this should be lower than or equal to. Or if this is lower than, then this should be higher than or equal to. Equal. Yeah, I mean, you cannot formulate it really like this in this case. Okay, let me formulate this offline and update it again. So you can have, so this is just the, to the other group. Okay, this is just the two-sided version. And then you can also have one-sided versions of this, which would be that, for instance, the means of the mean of group one. Group one is higher than or equal to the mean of group two, which is now a one-sided null hypothesis. And then for the alternative hypothesis, then this should be lower than Okay, I will re-upload this, so if you don't have to take this note. So for all of them, for all of the t-tests, I will also add one-sided hypotheses here. But I hope it makes sense. So when the sign lower, high, yes, Nastya, that's correct. If you have directionality, then this is a one-sided test. Are you going to be allowed a cheat sheet? It's not going to be your own cheat sheet, but if you need to answer questions based on formulas, etc., we will provide you with that. So that will also be a part of, for instance, a practice exam that we will provide you. So the two sample t-test versus what's called a Welch test. Okay, so in the case of independent sample t-test, you need to say something about the equality of variances between group 1 and group 2. Okay. If you can assume that the variances are equal, so we are testing the means, but we need to talk about the variances because this is how there are different calculations of test statistic if you have different variances between these two groups, or if you can assume equal variances between these two groups. The way we do this is if you have equal variances, then you can use this two sample t-test. And if you have unequal variances, then you use a Welch two sample t-test. So this is the default option in R. And we will see how you can also use equal variances option in R. But it's important for you to know that to decide, you need to use what's called a Levene's test. So I hope I'm not overwhelming you, but basically before doing a two sample t-test, independent sample t-test, the first step is actually to do a Levene's test to see if the variances between these two groups are equal. So the null hypothesis of the Levene's test is that the variances are equal. And the alternative hypothesis is that variances are unequal between these two groups. So if you have a low p-value, so lower than your significance level, then you will reject the null hypothesis, meaning that you need to assume that the variances are unequal, which means that you need to do an unequal, you need to do a Welch two sample t-test. If the Levene's test actually gives you a high p-value, then you do not reject the null hypothesis. And then in this case, you need to go to equal variances to sample t-test. Okay, I hope that makes sense. Let's look at these in an example. So this is a Colgate ad, and then you have the world of healthy smiles, but you depict a picture of a woman without teeth. And then this is called basically a cynical humor. And then the goal is here to assess the effect of cynical humor in ads. We collect, or they collect, data where like from 226 people, and 109 saw this ad, which would be then the treatment group, and 117 did not see this ad. So we want to understand from the people who saw the ad, which means that they have seen the cynical humor, versus like we want to understand how how the attitude towards Colgate is affected if they see the cynical humor ad or they didn't see this. So in this sense, we have actually two groups, right? Two different groups of people or different groups of subjects, elements. that we want to compare based on this attitude towards Colgate. And then one group see the ad, the other one didn't see the ad, which means that we need to conduct an independent samples t-test. If you want to see the means across different groups, so if you want to see the mean of a metric variable across two different groups, then you can use tapply, right? You give the basically the metric variable, the group variable, the function that you want to execute, and then this removes the NAs in the data. You have already used tapply in the assignments, right? So here we see that the no ad, the attitude towards Colgate is actually higher in the case of no ads. So the cynical humor, yeah, maybe it didn't work really well. But this is just descriptive from our sample. We can also look at, for instance, standard deviation that in this case, when people saw ads, their opinions differed more than when they didn't see the ads, because the standard deviation is higher here, right? Like there is more variation in the opinions there. If we look at the box plots to see the distributions, we also see that the medians are different, but the distributions themselves doesn't seem to be that, I mean, like at least they cover the same areas. So as I said, like the box plots focus on median and variation. You can also do a bar plot where you can just report the means. So in this week, you will also have a plot. So you can just use these codes to do the assignment. Can we explain the standard deviation of the ad again? Yes, I can. Okay, so here we saw that the mean attitude towards Colgate is actually higher in the condition of no ads. So when people didn't see this cynical humor ad. When we look at the standard deviation though, if the standard deviation is lower than, like, we see that the standard deviation is lower in the case of no ads, meaning that there is less variation, because as if you remember, standard deviation is the square root of the variance in the data. This indirectly means that we see we see a higher attitude towards Colgate, and this is actually more consistent across the participants. But in the case of like in the case when they see the ads, we both see a lower attitude towards Colgate, and but the opinions are more diverse compared to, of course, the no ad group. Does that make sense? So it might be that some people actually enjoyed the advertising, but on average, if you account for all people, then it looks like the ad didn't work, at least from the descriptive. So we are not doing a rigorous testing here. Okay, so we first look at the two sample. Yeah, we first look at both of the tests. As I said, we have a two sample t-test, which assumes equal variances. And then we have a Welch t-test, which assumes unequal variances. Here you see the coding for both of them. Notice that's the default option. So when we didn't specify this var equal parameter argument in the function, then the default is false, meaning that we end up with a Welch two sample t-test, meaning that we don't assume the variances are equal between the people who didn't see the ad and who saw the ad. Okay, so if you actually look at the results of this, they're pretty close, but notice that the p-value Yeah, what does the var equal to t? This t means true, okay? So in R, the capital T, if you put like this, it will actually change colors. You can also just say true. It is equivalent. This means that do we assume the variances are equal? True, meaning that, okay, we assume the variances are equal. In this case, the default option when you don't write anything, or you can just write var equal to false here. Then you assume that the variances between two groups are not equal. Here we observe slight difference between the p-value, but in some cases, this can actually be larger. So we really need to pay attention to this equality of variances before we actually do the t-test. So it's important for the purpose of the course that when you see two outputs of t-tests, or Welch t-test or two sample t-test, that assumes equal variances, which one to actually use. And for that, we use a Levene's test. Levene's test is within the CAR library. And then you simply, sorry, I also didn't explain this part, right? Sorry for that. So when you have two sample t-tests, we first provide the variable that we want to calculate the mean for. So we are interested in the mean attitude towards Colgate here. Then you put a tilde here. This is a tilde. So this basically splits the data into the groups that we have. And the group, remember, it was people who see ads or who didn't see the ads. And I would always suggest you to use the factor because in some cases, this group variable might be just numeric, and then you might calculate something different here. So always use this factor within this function to make sure that you're actually using this group variable as a grouping variable, as a non-metric variable. So one of the differences between the two sample t-test and the Welch test is that for two sample t-tests, the variances are equal, and for Welch, it's not. Yes, that's true. This is basically how all of this statistics are calculated. Whatever you see here, the t-value, and then degrees of freedom and p-value, in this case, it accounts for the inequality of the variances. If you see these numbers are different, although quite close to each other, these numbers are all different. And the Levene's test, in this case, as I said, this Levene test function is a function in the CAR library. Here you provide the dependent variable and the grouping variable with a comma. Okay. As you've seen, this is again factorized because we want to make sure that we are using these as non-metric variable, even if they were coded as 1, 2, 3, for instance. Sorry, 1, 1, 2, because this is a t-test. And in our output, we again get a p-value. So this is an f-test, meaning that the p-value is that this f, like we are higher, like the area between area more extreme to the f test statistic that we observe from our data. In this case, we see this p-value is actually higher than 0.05, meaning that we do not reject H0. And remember what the H0 was? In the Levene's test, H0 is that variances are equal. As always, by the way, this is a null hypothesis, so the equality is in the null hypothesis, so it's not hard to remember. And you know that the Levene test is related to variances. So variances are equal, variances are not equal. If we don't reject H0, this means that we, the variance between the treatment group and the control group, meaning that the add group and no add group, we can assume that that they are equal. So the correct test to use is actually the correct test to use is the two sample t-test here. Yes. And then from this, we can conclude that the p-value is less than 0.05, our significance level. Then in this case, we reject H0 of the t-test, meaning that the means are different between these two groups. Okay, let's see. First we do Levene's test, then the variances are equal t-test. Yes, that's correct. Is there a break? Let me go over these one-sided t-test and then we take a break. Okay, I now want to show you this one-sided t-test. We will do the same two samples t-test. So don't confuse them with each other. We are talking about independent samples or two samples t-test, but we can, our hypotheses can be one-sided or two-sided. In this case, we are interested in, based on some theories in the literature, the researcher expects that respondents that see the ad with cynical humor report a more positive or higher attitude. So our expectation somehow is that this mean of the treatment, so people who saw the ad would have a higher first attitude towards the Colgate versus people who did not. Here, then we assume a directionality, right? Or we are testing a directionality. And then in the null hypothesis, this is the other way around. So the mean in the treatment group is less than or equal to mean in the control group. The level of significance is 0.05. Okay. If we quickly go over this. If you remember, again, the t-test function, for all of t-tests, you use the same function, but the arguments can differ. We again have the variable that we calculate the mean for, tilde the grouping variable. In this case, it's we factorize it using factors so that we make sure that this is counted as a non-metric variable. Then the important critical part in a one-sided test is that we specify this alternative argument here. And in this case, we say less. Remember that alternative is equivalent to alternative hypothesis, and our alternative hypothesis was that the mu treatment is greater than mu control. But the way this works in R, deciding like greater or less, I basically wrote everything here so that you can go back to this like also while doing the assignment and really grasp this for yourself. But the decision between greater and less depends on how R orders this the levels of this group. Okay. In this case, under the group, we have no add and so add, apparently, okay? And R always order these as with alphabetical order, meaning that if you look at the categories within this group variable, it will first get the no add and then get the so add. then it will read this noadd minus soadd, okay? Because we look at the differences. So it puts the noadd, the first one alphabetically on the left-hand side and the second one alphabetically on the right-hand side. Hence, the alternative is then noadd minus soadd is what then 0? It should be less than 0, because if this is less than 0, then we achieve the alternative hypothesis stated here. So this is add, this is noadd, and the noadd minus soadd, so if you just put this on this side, is actually less than 0. Okay? So that's why we actually use less here. And once you like do this correctly, then the rest is quite straightforward. You simply focus on p-value. In this case, we see that the p-value is actually greater than 0.05. It's actually 1, like it's very high. So the direction is actually opposite than what we see in our data. We see in our data that the mean in group soadd is less than the group without add observation. So overall, in this case, you do not reject H0 and conclude that in this case, the attitude towards Colgate, the mean attitude towards Colgate is for people who solve the ad is less than or equal to the ones with who didn't see the ad. Okay, so you can also see a more like full explanation here for yourself. So in general, for each version of t-test, you use the same function and you only diversify by the use of equal variances or amount of variables. Yes, so there are actually, we have seen so far three parameterizations in a way. The first one is that you only use one metric variable and mu equal to, which would be a one sample t-test. The second one is that you have two sample t-tests or independent sample t-tests where you put a tilde here. The third one, and then this would be a two-sided test. The third one is that if this is a one-sided test, you use an alternative argument, and the var equal to true or false is related to if you can assume the variances between the two groups are equal or not. With less or and more. Yeah, okay. Yes, I will. So in R, what happens is we have our grouping variable. R reads this grouping variable first and like basically understand the levels of it or categories under it. The first category for R is the first one that comes alphabetically first. So in this case, we have noadd and soadd in the data. Okay, when you open this in R, we see under group column or variable noadd or soadd. In this case, R orders them as noadd and soadd. So the noadd comes first, and it puts in a way it puts a difference sign in between. So it subtracts noadd from soadd. What does it subtract? The mean of attitude. Then you need to decide based on your hypothesis or based on your alternative hypothesis whether this difference should be less than 0 or more than 0. If this should be less than 0, then you put a less. If this should be higher than 0, then you should put a greater here. So the options for alternative is greater or less. Okay, now, yes, we will look at ANOVA. Before you go, I want to make a quiz, then we can take a break. So I see the time is 10 right now. I will set it to, let's see. So I will set the quiz time to 12 past 10, to just give you 2 more minutes, or actually give myself 2 more minutes because I need to set it. Okay. Give me a second. It will be available soon and I will let you know when exactly it's available. Okay, 12 past 10. Okay. So now it has become available. You have 10 minutes. If you go to modules, it's under week 2. So just to show you, it's here. Sorry, it's under week 3. This is quiz 2. And it will be closed at 12 past 10. And after that, let's meet at 10:20.
Okay, let's.
Yeah. Okay, now let's continue with ANOVA. And ANOVA is basically an abbreviation for analysis of variance. We analyze variances, but we are still interested in comparisons of means across groups. So when we have, in the t-test, we had 2 groups, right? When we have actually 3 or more groups, so actually technically, yeah, and then more than 2 different groups, then we use an ANOVA. So if we have 3 or more groups, we use an ANOVA to compare the means. And in essence, this is a one sample F-test. And with the hypothesis, null hypothesis is that the means of the groups are equal, and the alternative hypothesis is that the group mean of the groups are not equal. And this is a joint test. So we are actually looking at if all of these means for all of the groups are equal or not. The intuition behind the ANOVA is that here you can see this calculation of F statistic here. And then, but I want to focus on the intuition that we call this it as an analysis of variance because this is a comparison of between variance with within variance. What do I mean by that? So here you see 2 situations. We have 3 groups, and we want to understand if the means of these groups are different from each other. In the case of A, here these dots represent the means of their distribution. So these are the kind of data distributions that we observe. And then the variance between groups are actually related to if these mean for each group is like, are they far away from each other or not? And the variance within group is within one sample, meaning that within one group, how variable is the observations. And here you see that variance between, like if you compare A and B, here you see that the variance between groups is actually smaller than variance within group. And if you actually compare this two, then we will get a low F value, meaning that, and you can also see in the pictures that these means are actually very close to each other. And we see a lot of observations actually meshed into each other. So these can actually come from different groups. So an observation here in this point, for instance, can come from any of these groups. So this is very much likely, meaning that also the F statistic is low, meaning that the means are actually not different between these 3 groups. But if you compare, if you look at the situation B, here we have the variances between groups very large, but variances within groups are actually very low. So you see the separation of these 3 groups in terms of their means. So this is kind of the intuition at the back of ANOVA. This is how we use variation to compare means. The example here includes a manager who wants to increase employee productivity by using a spreadsheet program. As he does not have the skills in-house, he employs an external agency that provides training in this spreadsheet program. They offer 3 courses, a beginner, intermediate, and advanced course. He is unsure which course is needed for the type of work they do at his company. So he sends 15 employees to each of these courses. When they all return from the training, he gives them a problem to solve using the spreadsheet program and times how long it takes them to complete the problem. He then compares the 3 courses to see if there are any differences in the average time it took to complete the problem. So we will actually, the question then is, do these 3 groups differ in the average time they took to complete the problem? And we have a 0.05 significance level. You can like the descriptives and plots are basically quite similar to what we have already seen for the t-test. So you can check these on your own, but we can see that the means are actually not that different, mean times from the bar plots. For ANOVA, we use AOV function in R. And apparently in this data set, the test time, so the time that's spent to complete the task, is recorded in test time column. And then we have a groups column again. Note that we, again, have the factor. So this is kind of a warning again that makes sure that you use factor for the grouping variable to make sure that R records this as non-metric. And from the summary of ANOVA, so we, when you just run ANOVA, it doesn't give this output, but you need to save it in an object and get the summary of this. When you have the output, you focus on this p-value. So probability that F is larger than the statistic actually is, in this case, we see that this is less than 0.05. So our decision is to reject null hypothesis. And remember, what was it? All groups have equal means. So we reject this and conclude H1. And this means that at least one of the groups differ in time it took to finish the test. So it's very important to see in the case of ANOVA that yeah, so this just summarizes what I said. But in case of ANOVA, it's very important to understand that this is a joint test. When we reject H0, it doesn't mean all of the means are different from each other. It means that at least one of them is different from the others. So there is a difference, okay? So it might be that two of these, like let's say beginner and intermediate means are actually quite close. But if advanced mean is very different from the two, then ANOVA will still reject the null hypothesis. Okay. And yeah, as I said, then this is a kind of a problem that we actually don't know which group exactly differ from each other. For that, we can do a follow-up test, which is called 2K-HSD test. And this basically does separate t-test with some adjustments. We don't cover that here necessarily, but you basically put the ANOVA object that you created here. So this is the result from ANOVA using 2K-HSD function, which gives you this output where you see for each of the levels within within the grouping variable. So this is the course that these people take. And then you see the separate tests for each couple of these categories. So here, for instance, intermediate versus beginner. So this is the difference between intermediate and beginner. And we see that the p-value is less than 0.05. So we can actually conclude that this is a significant difference. Okay, so we reject the null that this is 0. We can conclude that this difference is significant. And this difference is minus 2.5, meaning that when I take the mean of intermediate and subtract the mean of beginner, I see minus 2, which means that actually in the beginner group, the time it took to complete the task is higher, right? So intermediate minus beginner is negative 2.5, meaning that beginner minus intermediate is actually 2.5. And this is significant. The second one is for the advanced versus beginner. This is again significant and negative, meaning that again for also advanced, the difference between advanced and beginner is minus 2.9, meaning that it took beginners 2.9 more time, 2.9, I think it was minutes more than advanced people, the people who follow the advanced course. But when we look at advanced and intermediate, we see that the actually p-value is above 0.05. Although we see this difference of 0.4 minutes, this difference is not significant. So we can conclude that there's no significant difference in the means of advanced and intermediate, which gives us an idea that actually the difference, like the ANOVA test, in ANOVA we rejected because apparently the beginner group differs from the others and not advanced and intermediate groups. Okay. So the difference between t-test and ANOVA is the amount of groups. That's true. Yeah. And in ANOVA, you also assume equal variances, just so you know. But there is no other way to execute ANOVA, so that's not really relevant. For you to distinguish between t-test and ANOVA, yes, indeed, you look at the number of groups. Let's now look at the correlation analysis. And you already probably know that correlation correlation means that we are looking at the association between two metric variables. So we will look at how, basically a DV and IV are related. Actually, in the case of correlation, we cannot talk about causality of the two. For that, we will look at regression. But basically, this is in correlation, we will look at an association between the two metric variables. That's important. And for that, we use a correlation coefficient, which is specifically Pearson's sample correlation coefficient. It looks at the direction and strength of linear association. This is very important. The regression, we will look at it next week. So I think that's a better place to talk about the difference between correlation and regression, correlation analysis and regression. Okay, so as I said, direction and strength of linear association. That's important. And this correlation coefficient is always between -1 and 1. And if it's minus, then we call it a negative correlation. If it's positive, it's a positive correlation. It's also symmetric, meaning that the correlation between x and y is the same as y and x. So like there is no difference if you first take x or y, basically. Okay. Yes, you can check this formula on your own. As I said, Pearson correlation is related to the strength and direction of linear association. So this is a very important point. Here you see a bunch of scatter plots between two variables. So this is the x variable, this is the y variable, basically, for all of these plots. You see different patterns of data. And this goes from, for instance, perfect correlation, perfect positive correlation to perfect negative correlation. And as you can see that these are very much closer on a line because the correlation coefficient looks at the linear associations. If we have a flat relationship, there is actually, you cannot calculate correlation coefficient. And if we see different kinds of patterns which are not linear, then correlation, like the Pearson correlation coefficient, will be 0. So beware that when we talk about correlation, we only talk about linear associations and not nonlinear associations. As you can see, these are all pretty interesting patterns, and apparently, like it's clear that there is a relationship between these two variables, but it's not a linear relationship. And for the for direction, you can see that this is a positive slope. This becomes negative slope when we have negative correlation. And for strength is determined by how close the points accumulate on a line. So here you see that this is 0.8. You start to see a clear line. This is perfect. And if this is just a random cloud of points, then this is zero correlation. So this picture is a good way to actually understand what direction, strength, and linearity of the correlation means. Okay, when we talk about correlation, of course, the immediate thing is to also talk about causation, because correlation does not mean causation. Here you see, and we already talked about this in first week, right? So what is the conditions for actually claiming a causation? So here you say that a news related to when ice cream sales rise, so the homicide coincidence, or will your next con murder you? In this case, of course, it doesn't make sense that like the ice cream sales will actually lead to homicide. This is both are actually affected by the weather. So when it's warmer, when it's hot, people do buy more ice creams, and they also the rates of homicide also increases. So there is another confounding variable, like there is a variable that affects both of these variables, which causes them to actually increase. So that's the causal relationship. But the ice cream sales versus the sales of ice cream sales versus the number of homicides, they just move together, but they're not causally related. You can also check this example where we see, okay, this is not the, where you see the number of storks, humans, and birth rate. And apparently in Turkey, you really have high number of storks and birth rate, but these are obviously not causal. So this is just another example. And then we can look at an example for the correlation analysis. Here, you have data related to, you make measurements from people related to their viewing time, irritation, and age. So viewing time means viewing time of commercial until you zap to another channel, and irritation from the commercial. So 1 is not irritated at all, and 7 is very irritated. So when you look at the viewing time and the irritation, you can see that in the scatter plot, it looks like there's a negative kind of slope that you can fit among these points. But it's also not super clear if this can also be seen as a normal, as a random cloud. So for that, we can look at basically, so if we want to understand how strong is the correlation between the degree of irritation for commercials and the viewing time for commercials, then we can do what's called a correlation test. And the correlation test, in the null hypothesis of the correlation test is that the correlation is 0, and then the alternative hypothesis is that correlation is not equal to 0. So there is a significant correlation. You use this core test function to do the correlation analysis. So you basically put the first metric variable and the second metric variable that you're interested in. And from the output, as always, we look at the p-value. And in this case, p-value is even smaller than 0.01. Depending on your significance level, we tend to say it's 0.05, but you will be always given that information. And then we can reject H0, meaning that we conclude that the true correlation is actually not equal to 0. It's different than 0. And in this case, indeed, the correlation is apparently negative 0.68. Here is an important thing. It's important to see that the significance of this test does not mean that there is a substantive correlation. In this case, the correlation coefficient is indeed above 0.6, which is in the high levels, but it might be that this correlation might be 0.02, but you might still get a significant correlation. So the statistical significance doesn't mean that this correlation is very high. Yes, here alpha, you can think alpha as 0.01 or 0.05, it doesn't matter. In this case, I forgot to specify it on this slide, basically. But even if it is 0.05, you would have rejected the null hypothesis. Okay, so then one other important thing is that we see correlation, but it might be that another variable might be affecting both of these variables, and it might create this what's called a spurious relationship. And let me try to show you what might be that relationship here. So we talked about weaving time and the irritation. It might be that increasing age might be related. So the age and weaving time might actually move together. So as you age, you have more time to, let's say, kill, and then you watch more and more. So sorry, this is actually, it's not you watch more and more, but you basically also watch the commercials. So you are, let's say, more patient in a way, that you watch more commercials before you zap to another channel. It might also mean that, yeah, it might also be that because you are, let's say, older, it's like you get less irritated by the commercials. Like you don't really care about commercials that much, so you just watch them and you are less irritated, so you don't also zap. This might actually mean that age is a correlating variable for both of these variables. And if we are blind to the age, we can see a correlation. But once we actually control for the effects of age, or the association of age with these two variables, it might be that there is actually no association between irritation and weaving time, as we have concluded before. In this analysis, we concluded that there's the correlation of minus 0.6768 is the correlation, and this is a significant correlation. And in this case, we want to understand, controlling for age, do we see still this correlation? So this is called a partial correlation. So this is a measure of the association between the two variables after controlling or adjusting for the effects of one or more additional variables. In this case, we will now look at if when we control for age, do we still see this correlation between the two? So the question is, how strong is the relation between the degree of irritation for commercials and the viewing time for commercial if we control for age? In the partial correlation test, we test if the partial correlation is significantly different than 0. So it's quite similar to the regular correlation test, but in this case, we are interested in the partial correlation. We use this pcore.test function from ppcore package. You will have all the details in the assignment. This pcore test function takes first the first metric variable that you're interested in, second metric variable. So this is basically the correlation that you want to understand, controlling for the third variable that you put here. So controlling for age, do we have a significant correlation between irritation and viewing time? Then here we see that the partial correlation is negative 0.3, which is way lower than the correlation of 0.6 that we have seen before. And the p-value is that we do not reject H0, right? Let's say we have a 0.05 significance level. So the conclusion is that the partial correlation is not significantly different than 0. So once we actually account for age, irritation and viewing time for commercials are not associated, right? Because we couldn't reject the null hypothesis and conclude that this partial correlation is different than 0. This actually means that there is indeed a spurious relationship between the viewing time and irritation. And that's kind of related to a third variable, which is the age. So to be able to understand if you have a spurious relationship or not, you first look at the correlation test and see if there is a significant correlation to even to start talking about an association. And then you look at this additional, the effects of an additional variable. In this case, it was age. And then see, even when you control for this variable, do you see a significant correlation? If you don't see a significant partial correlation, then this means that there is a significant correlation without this, but there is no significant correlation with this variable, meaning that the relationship, so the association that you're after, which in this case is the weaving time and irritation, is actually a spurious relationship. Okay. So with that, we came to the end of this lecture. Next time we will look at regression. If you have any other questions, you can post them now. I can stay a bit longer.